About today's experiment. Uh, what are some of the hazards for today's experiment? Hydrochloric acid. I think everybody's worked with hydrochloric acid before, right? What should you do if you spill some on your hands or what? Just rinse. How long are you supposed to rinse for? Was it 10 minutes? Is it? How long are you supposed to irrigate? Let's say some splashes in your eyes. How long are you supposed to irrigate your eyes for? 10 minutes? How many people say 10 minutes? 15 minutes? 20 minutes? 30 minutes? Okay, maybe I have to show the safety video because you guys don't remember, do you? 15 minutes, right? 15 minutes, so we'll be showing the safety video sometime. Also, you know, safety questions are fair game for quizzes too, and exams. Hopefully you don't splash in your eyes because you brought your goggles today, right? And then it should prevent. What else are we working with? We're working with barium chloride. Barium chloride. You know, avoid contact with that. You know, you don't want to spill any on you. Barium chloride is actually toxic. Although they give, you know, barium sulfate as an imaging agent. People drink barium sulfate before they go and get it like a CT scan. Maybe they don't use barium sulfate. They use iodine, I think, now. You might have had a barium cocktail. A good contrasting agent. But barium chloride, the difference between barium sulfate and barium chloride has to do with solubility. You know, sodium hydroxide, what is that? This is a strong base. You know, it's drain cleaner. But people, do you know people drink magnesium hydroxide? Would you drink sodium hydroxide if you ran out of magnesium hydroxide? Let's say I ran out of magnesium hydroxide, milk and magnesia. You know, I have an upset stomach, so there's a bottle of drain cleaner, has sodium hydroxide, same thing, right? Sodium hydroxide, magnesium hydroxide, both should work because they both contain hydroxide. Yes or no? No, and then prove it. Why? Why not? Why not? Why not drink sodium hydroxide? Sodium hydroxide, magnesium hydroxide, same thing. Yes or no? No, but why? Hopefully, yeah, I'm glad. You know, common sense tells you they aren't the same thing. That's good. You know, but maybe there's some pharmacist out there with no training or anything like that, doesn't care, grabs the bottle of drain cleaner because he sees hydroxide, thinks it's the same thing. You know, hopefully not. But why do you think that is? Why do you think barium chloride's toxic, whereas barium sulfate's not going to kill you if you drink it? Well, everything can kill you, including water. You know, water. It's kind of funny because some cities in California, I think 2 of them, banned dihydrogen monoxide, you know, as a toxic chemical. There's some kind of hoax website that came up about the dangers of dihydrogen monoxide. It was a joke, you know, they're saying it's lethal, which is true because you can drown, right? And so some city council members were convinced that it should be on the list of banned chemicals for their city, trying to protect their citizens. Anyway, well, do you guys remember solubility rules? How many of you had to memorize your solubility rules in Chem 4? Very few. You know, that pays off. If you had to memorize it in Chem 4, then rememorizing them in Chem 1A is easy if you've forgotten them. For those of you who have to start off fresh and memorize them, you know, it takes time. You want to drill yourself with those solubility rules until you get them down because you're going to be expected to know those by exam 2, or the solubility rules. And so if you're slow at memorizing things like I am, I would jump ahead. Jump ahead to chapter 5, or it's in our lab manual. The lab manual ones are easier to memorize. And so I'd use the ones in our lab manual, the Chem 4 lab manual. The Chem 4 lab manual one's fine, but you will have to have those memorized. Just like nomenclature, if you don't have your solubility rules memorized and you don't know nomenclature, you're going to have a struggle in this class. Well, magnesium hydroxide is what we call an insoluble hydroxide. Sodium hydroxide is a soluble hydroxide, and it has to do with how much hydroxide content you have. The magnesium hydroxide will release it slowly because it's fairly insoluble, whereas the sodium hydroxide, it immediately releases. Same thing, barium sulfate. Barium sulfate is insoluble. Barium's the toxic agent. Sulfate's not super toxic. Whereas barium chloride is soluble. So the concentration of barium ions that you get in barium chloride is much higher than what you get in barium sulfate. In fact, barium sulfate is highly insoluble. And so even if it hits the stomach acid, it really doesn't dissolve very easily. Well, anyway, what we're doing today is called gravimetric analysis, and gravimetric analysis takes advantage of solubilities. Solubility rules, that kind of thing. The solubility rules that you learned in Chem 4 are very qualitative. We want more quantitative ones, but we aren't going to really dig into that until Chem 1B. Oops, sorry. So what are we doing today? Well, now we have an unknown, and this is unknown solid. I'll just write it out. In this unknown solid contains some amount of sulfate ions locked up in the solid state. What does that mean? That means that, the sulfates are bonded to what? If we have anions, we got to have cations. Now, it depends on what cations we have, because, does anybody remember the solubility rules for sulfate? Can somebody just rattle them off for me? Sulfates are all well, who wants to volunteer? Sulfates are all okay. See, so probably best to start reviewing ion formulas, names, and solubility rules now, so that you don't have to cram them in before the test. Okay? And so sulfates are all soluble, except for which ones? Not calcium, barium. They're all soluble. Oh, except for, yeah, calcium, barium, strontium. What else? Calcium, barium, strontium, mercury, silver, and lead. Is that from memory or from the chart? Okay, that's good. You got it. Yeah. All right. And so if this sulfate is paired with one of those ions, is it going to be easy to dissolve in water? No, because it's insoluble. And so if this sulfate is paired with like calcium, we're going to have a heck of a time dissolving it. Why do we need to dissolve it? Because in order to analyze the sulfate, we got to separate the sulfate from everything else. And so how do we separate the sulfate from everything else? Well, we dissolve it. Well, how do you dissolve it? Typically, we can try dissolving. When we dissolve solids, we try dissolving in water. If water doesn't work, we use hot water. If hot water doesn't work, we use maybe alcohol. If alcohol doesn't work, we try hexane, because it might be nonpolar. And so we're trying polar: water, hot water, alcohol, hexane. Hexane is what? 6-carbon alkane. It's a straight chain. If those don't work, then we try mineral acid. A mineral acid is like HCl, or acetic acid, some kind of acid to try to attack the solid to get it to dissolve. If a mineral acid doesn't work, then we try what's called an oxidizing acid. An oxidizing acid will, like we were talking about oxidizers the other day, we'll try to oxidize it to get it to dissolve. Mineral acids can oxidize as well, but not nearly as effectively as an oxidizing acid. And so examples of mineral acids would be HCl, HBrHI, acetic acid. Examples of oxidizing acids would be nitric acid, perchloric acid, those types of acids are oxidizing acids. How can we tell? Well, oxidation states tell us. It's pretty easy to tell a mineral acid from an oxidizing acid just by looking at the oxidation states in the acid. That's how we can tell. If oxidizing acid doesn't work, then we try hot oxidizing acid, hot nitric. You got to do this in the hood because you can generate some nasty fumes. So hot nitric acid sometimes works. If that doesn't work, sometimes we go to bases. You try different bases. All these reactions, you got to be very careful. You got to worry about explosions and that type of stuff because you don't know what's in an unknown, and so you have to be very cautious in doing these reactions. And so that's why you start off mild and then get more severe. And then you try bases. You could try bases like sodium hydroxide, etc. And if it still doesn't dissolve, then you have a headache. You have a big headache. Let me give you an example of a big headache. Most of the aluminum on Earth is in the ore called bauxite, which is aluminum oxide. Aluminum oxide doesn't dissolve in anything, basically. Well, the problem is you got to get it to dissolve, or you got to get it to melt in order to extract the aluminum metal out of aluminum oxide, right? Unfortunately, you can't melt the stuff. Even in a platinum, you know how hot a platinum furnace can get, or a fired furnace? They don't get hot enough to melt the stuff. It just doesn't melt. And so in order to process, you could get extreme temperatures maybe, get it. In order to process that, the aluminum oxide, it was very expensive. So aluminum used to be a very rare metal. Extremely rare metal until somebody found something that dissolves aluminum oxide. And they made a fortune on that. But anyway, if it still doesn't dissolve, then we got a headache on our hands, and it's hard to process. And so one of the steps here in our analysis is we're adding HCl. And this is the difference between Chem 4 and Chem 1A. Let me tell you about pre-lab quizzes. Pre-lab quizzes don't ask you, how many milliliters of HCl do you add at this step? It's not simple memorization like this. Pre-lab quizzes eventually, not at this level, but pre-lab quizzes eventually are going to ask you, what is the purpose of adding HCl? And so when you're writing out the procedure, obviously we want to cookbook this. We don't want to think because we just want to do it rapidly, collect our data, and then move on. But we're also going to have to think about this. Well, when you do your notebook prep, you don't add all these details. You could add them on the opposite page, the page where you scribble your notes, as you're thinking about this. But in the back of your mind, you might think, why am I adding the HCl? And so is the purpose of adding the HCl to help dissolve the solid? Well, did anybody read the write-up? The part where they're discussing the chemistry that's happening, or did everybody just read the procedure and write down the procedure? Or how many of you prepped your notebook? Just curious. How many people prepped the notebook for today's lab? 1, 2. That's on the low side, you know. Two, just two people? Three? Three people? Why is that? Why is that? Well, anyway, this lab is important because this lab you're going to write a formal report for. And the formal report isn't saying, oh, I added 15 milliliters of HCl. The formal report is much more in-depth. Okay? And so anyway, what was the purpose of adding the HCl? The purpose isn't to dissolve it, because these all should dissolve in water. So what we're going to do is we're going to dissolve this in water. When we dissolve this in water, if it's soluble, what forms? You know, well, obviously this must be what kind of solid? Kind of solid is this? You know, a lot of people, I know a lot of people over the semesters, this has happened to me many, many times, that, you know, people will start asking other people in class, did you do this? Did you do this? And then they try to lower everything. Like, okay, I'm not going to bother doing this because nobody else did that, right? And they're thinking, okay, that's going to make the C range, you know, the average. If everybody doesn't do it, then how can he fail everybody in the class? You know, but it happens, you know, if everybody doesn't do it, you still can fail everybody in the class. And so don't think that, okay, if everybody else is not doing it, I'm okay. No, because you don't want to sink. You know, when I was a student at UC, they were always talking sink or swim. Sink. Have you heard that, sink or swim? I was tired of sink or swim. But they're saying either you're going to drown or you're going to stay afloat. And so if everybody else is drowning, you don't want to join them. Don't think that way. You know, I don't know how many people are thinking, oh, you have to lower the C because, you know, nobody did it. Or if everybody did bad, then, you know. And so make sure you don't fall into that thinking. But anyway, today I was expecting prep, but we'll take a look at your notebooks. Just to see. Sulfate is going to be freed up into the aqueous state now from the solid. So solid, what does solid mean? It's locked in a lattice. In solids, there are different kinds of motion. We have vibrational and translational and rotational motion. The difference between a solid and an aqueous or liquid is that there's translational motion. It can move from point X1 to point X2. And I skipped that in chapter 1. But solids are locked in position, they can vibrate, etc., but they can't translate. Okay, now this is translating. There are cations in here, right? Okay, now we add the HCl. Why are we adding the HCl? Okay, that's an important question. Why are we adding the HCl? The reason we're adding the HCl is to prevent interfering ions from screwing up our analysis. And so this is called, we want to prevent interferences. In any kind of analysis, you always have interferences because things, you know, there are other things that can get mixed up in there, and it's an unknown, and everything's possible, right? And so what are some of the interfering ions? Well, we have to see what our analysis involves. You know, once we free up the sulfate, okay, so we free up the sulfate from the unknown solid. Now it's in the aqueous phase. Now it's independent, right, of the other ions. Now what we want to do is we want to capture the sulfate. How can we capture the sulfate? You know, well, we're going to precipitate it out. And what's a good precipitating agent for sulfate? Barium ions. And so the HCl, and then we add our barium chloride, AQ. Barium chloride AQ, you know, consists of barium ions and chloride ions. And so these barium ions are going to capture the sulfate ions, right, to form a precipitate like this. The crystals that form from this are tiny, and we get what we call a cloudy precipitate. And so we capture that. When they're tiny, they can stay suspended. Depends on how big they are. But if they're tiny, it takes a long time for them to settle, right? Long time for them to settle. But unfortunately, our crystals are going to be exceptionally tiny. Exceptionally tiny crystals are called colloidal, and they've reached this point where they're too small to settle. Just the kinetic energy in the water just keeps them permanently suspended. And so, for example, in milk, you know, milk, can you see, milk is like this cloudy suspension of stuff and it just doesn't settle. It stays permanently suspended. And so we have a cloudy precipitate that is colloidal. This makes it very difficult because the thing is, we have to capture 100% of the sulfate. In order to capture 100% of the sulfate, what should we do? We should make sure we add enough barium. But how can you tell when you've captured 100% of the sulfate? How you can tell is it should stop precipitating. Unfortunately, what happens is this gets cloudier and cloudier, and so with each extra drop of barium chloride that falls in here, you don't see anything. You know, it's like this thick fog, and you can't see if it's getting foggier or not by the drop. And so it's extremely difficult to see. Some things help. You know, some things help growing bigger crystals. Do you want to do a slow addition of barium chloride to get bigger crystals, or rapid addition of barium chloride to get bigger crystals? These crystals are tiny right now. But what do you think would help promote the growth of bigger crystals? A slow addition of barium chloride or rapid addition? What do you think promotes slow growth, promotes these big crystals, or rapid growth promotes these big crystals? It's actually slow growth that promotes this. Slow growth is because there are two processes that happen in crystal formation. One process is called nucleation. Nucleation is growing like a baby crystal, and certain things help nucleate crystals, like scratches in the beaker or seed crystals. You know, they have what's those? You know, in certain areas where they seed the clouds. Have you heard that? Because no. Well, anyway. What we want to do is we want to prevent too many crystals from nucleating, because if you have a ton of crystals that nucleated, then they can't grow so big. Right? What we want to do is we want to minimize nucleation. We just want a few crystals to nucleate and let those grow slowly into large size. And so normally we try to prevent nucleation, making sure everything's clean and you don't add too much dust or anything else to it. And let those grow. This is still going to be difficult, but you know, it's better if you could get bigger crystals, because then what happens is they settle much faster. And so you'll notice that, oh, hey, my neighbors have already settled, but mine haven't settled at all. Well, your neighbor had, bigger crystals. That's it. Okay. So anyway, we'll find out what your neighbor did, and then just try to repeat that. Okay, from this, well, it gets too cloudy. We can't see if we've captured all the sulfates. So what we have to do is we have to get this to rapidly settle. But how can you get this to rapidly settle? Because colloidal, you're going to be waiting here for years. Some colloidal suspensions will never settle. They're permanently suspended. And so how can you get a colloidal suspension to settle? These are all pre-lab quizzes, quiz questions. And normally, the labs that I took, there was no discussion. You went in, you took the pre-lab quiz, and then you started the lab. That was it. If there was a Q&A, but we had to use all the time for the lab. And they figured you can read, right? You could figure it out yourself. You don't need somebody here talking about it. In fact, I think that's one of the reasons why I don't like to talk too much about certain things, because it means that people get this sense that they don't have to read it because the teacher is going to discuss it anyway. Right? You shouldn't get into that habit either, because this is not like Chem 4 where the teacher is going to explain step by step so you don't have to read the lab at all. And so I start to veer away from explaining every single step and then expect you to figure it out. And if there's confusing things in the procedure, for sure, ask, and then I'll explain it in detail or demo it, But if there are no questions at the beginning, then I assume that the reading was okay and that you understand what's going on in the lab and you're ready to go. We'll talk about safety issues and then I'll let you go. And so this lab's a little unusual because I'm going to explain this in detail because, as I said, this is a formal report lab. You got to understand this in detail. And so, did anybody read, at least if you didn't prep your notebook, did you read the write-up? Okay. How many people read the write-up? All right. From the reading, did they tell you how we're going to get rid of this, or this suspension? We're going to get it to settle. How can we get it to rapidly settle? We're going to heat it. That heating process is called this is the symbol for heat, delta. We're going to heat it. We're going to heat it to a boil. And what's that going to do? What does heating do? Why does heating help get this suspension to settle? Yeah, they can collide with each other. These little crystals hit each other and then they stick to each other. You form bonds. Or, and as these collide with each other, they form bigger conglomerates, crystals. And once they reach a certain point, they get too heavy and they fall due to gravity. That's good. Do you know what that process is called? What is that process called? It's called, you could call it coagulation or digestion. And so we're going to call it digestion. And so what we're going to do is we're going to let this digest, and then, we heat it to a boil. And obviously, if it's on the hot plate, you heat it to a boil, bring it to a boil, and then take it off. Get it to a boil, and then cool it on a hot plate. Not a hot plate, but a ceramic plate. You don't want to leave it on there forever. Obviously it's going to digest better, but you got to finish this lab. And so these are hot plates here. Do you see the hot plates? We aren't using Bunsen burners. It takes too much time. Bunsen burners, you can only heat one beaker at a time. With a hot plate, you can heat all three at the same time. We used to do this lab in sequence. It'd take a long time with a Bunsen burner. People wouldn't finish. All right, hopefully heating this to a boil and then letting it cool down will coagulate the suspension so that this becomes a actually, let's use some symbols, CCS. Sulfates are colorless. I told you your unknown's white, so the cations are going to be colorless. And so CCS means clear colorless solution. Now, when we add our barium chloride, we can see. If we add our barium chloride, what you want to see is you want to wash it, hit the solution. Barium chloride is more dense than this solution. You know, barium chloride is fairly concentrated, and barium ions, look how heavy barium ions are. Barium ions are heavy. This is why they use barium, or maybe they used to use barium in CAT scans. They use them in CAT scans because, you know, things that are heavy, it's not because they're heavy. Things that have a lot of electrons absorb a lot of light, including X-rays. And so barium ions are good absorbers of X-rays, whereas lighter atoms are not. And so it's kind of funny. Barium is used as an X-ray absorber, whereas beryllium is used as an X-ray window. Beryllium. Beryllium, unfortunately, is also highly toxic. But there are a lot of beryllium windows out there for letting X-rays pass through. They're in the same family. Well, anyway, going to this, now we can see, but when this hits, the barium chloride is more dense, so it's going to sink in. And then, you know, obviously diffusion is going to take place, but it takes place slowly. Watch the barium sink through the solution and see if any cloud formation occurs. You know, they say add the barium chloride with stirring. And so what happens if I stir this? What happens if I stir this? What's going to happen to my nice coagulated suspension here? If I stir this, what's going to happen? It's going to get cloudy again. And so, you know, do not stir this. I guess the lab procedure should be rewritten. Get rid of that. That I think is a ridiculous step. Ridiculous step is to stir and add. You know why they want you to stir it? They want you to stir it to make sure there are no concentration gradients. A gradient is, you know, it's more concentrated here, less concentrated there, right? But, well, we aren't going to worry about the gradients. We're just going to watch this drop as it hits, and then if they're, you know, if it's more concentrated here, we're going to strategically place the drops. We're going to put a drop here, drop here, drop here in different parts of the solution, and then watch it sink. And in case there's a gradient, we'll see cloud formation in different spots. I doubt there's going to be much of a gradient after heating this, you know. But anyway, do not stir. Otherwise, you're wasting everybody's time, including mine, because you're going to be here after, and I want to leave on time, you know. Well, after my office half hour. You can stay till 5:35. Not 5:35. Don't stay till 5:35. You can stay till 1. No, make that 12:55 because at 1 o'clock I have a meeting today. So 12:55. If you want to, you really want to stir it. All right, so we watch this, and what are we looking for? We're looking for any evidence of precipitation. That's what we're looking for. Any evidence of precipitation. If there is precipitation formation, what do you need to do? And so we have a choice. We get precipitation. Additional. This is another difference between Chem 4 and Chem 1A. This procedure says to add 12 milliliters of barium chloride. 2 milliliters of barium chloride. 10? More if necessary. What does more if necessary? A lot of people only add 10 and stop. They might get lucky, they might not. you just keep adding. I don't care how much you have to add. You keep adding until it stops precipitating. Because your unknowns might have a little bit of sulfate. A little bit of sulfate means it doesn't take much. And so it could be a lot less than 10. You know, the thing is, this procedure is written for every single unknown out there. Well, not, because otherwise they'd say add 20, 30, 40. I don't know. They'd have to pick some big number. Because in case you have a lot of sulfate, and in case you overshot, in case this happened, you're going to be adding a lot of barium. And so the amount of barium varies. And so what you need to do is you need to add enough. And that could be less than 10, because if you add too much, you could run into problems of something called co-precipitation. Co-precipitation is unwanted salts co-precipitating out with your barium sulfate. It's talked about in the procedure. You don't want co-precipitation. If you add too little, then you're going to lose some of the sulfate, and your analysis is going to be a failure. And so you need to add enough. And so this is it. You ignore the 10, and you just keep adding until it gets too cloudy, and then you coagulate or digest, and then you keep adding until, well, let's say this keeps precipitating, then you just repeat. You keep repeating this process until this happens. No more precipitate. Once you get no more precipitate, then what we're going to do is we're going to do a final digestion step. The final digestion step is to grow the crystals big so they don't clog up our filters. Because filtration, we're using a filter made out of a ceramic disc. And the pores in this filter are extremely small. The pores on this are 1 micron, I think. I don't know how big. It's usually marked on here, but it's blurry. I can't read that. But look at, I'm going to pour some water in our filter. This is a ceramic filter. And I'm going to look at the bottom. And I don't see any evidence of water. Now I see. It's just starting to begin to get wet. Maybe we'll get 1 drop. Fall. Oh, this filter is not clogged. That's good. Because the drop, do you see a drop is forming? There. Okay, we got 1 drop through here. Can you imagine if you have tiny crystals that clog this, you're going to have to come in on a second lab day to finish your filtration, right? The people who have nicely coagulated crystals, they get out early, you know, it's fast. But normally on this day, I expect to stay late because there's always going to be people whose filtration takes like an hour for one. And then set it up. So we're going to do this final digestion step. So if we have no more precipitate, we do digest longer, as long as possible, you know, to get nicely coagulated crystals. Okay. All right, so what have we done in this process? What we've done is we've separated the sulfate from the unknown solid and then captured it and then isolated it. Isolated it as a precipitate. The next thing we're going to do when we come in is, actually we've got a little bit of time, is we're going to separate it from this mixture and wash the crystals. That's what we're going to do. Okay, but let's go back over here. Unfortunately, barium is not super selective. You know? Barium likes sulfate, but it also likes other ions. Does anybody know what other ions barium likes to precipitate with? based on solubility rules, barium also likes carbonate. Barium also likes phosphate. Anything else? Does barium like iodides? Does it like to precipitate with iodide? Bromide? Nitrate? Hydroxide? Hydroxide's borderline. Hydroxides are all insoluble except for group 1 ammonium and calcium strontium barium. And so I guess we won't include it here. Is it okay if we how can we separate these? You know, this is a white precipitate, this is a white precipitate, this is a white precipitate. How can we separate these three white precipitates? You know, there's a famous story about Louis Pasteur, who got some tweezers and separated out two forms of crystals from a mix, just one by one, picking out the crystals one by one. And so you could get a high-powered magnifying glass and some superfine tweezers and pick them out. Because they probably have a different crystal structure. You might be able to tell just based on the shape of the crystal. Maybe, maybe not. So how do you want to separate these out? Stanley? Yes. Because adding the acid is going to prevent these from forming in the first place, actually. They shouldn't form under acidic conditions because these precipitates are unstable in acid. And this is just a simple double replacement reaction. So, for example, if I have barium sulfate solid plus HCl, double replacement, tell me what my products are. Barium chloride and who said barium chloride? Yeah, that's right, and sulfuric acid. Oh, good. Barium chloride and sulfuric acid. What's your name? Jacob. And what's your name? Justin. Thanks. But what about this? So we have this double replacement. I just balanced it. These are all aqueous, and aqueous here. And then what do you do in a double replacement reaction like this? What's the next step? A double replacement reaction. But you separate the strong acid? We aren't going to do that yet. You mean do the ionic, get the complete equation, the ionic equation, the net ionic equation? Is that what you're saying? Yeah, we aren't going to do that yet because first we have to determine if there is a. Remember this, Jacob and Justin? Determine if there is a. Cecilia, you lose. What do you do next, Karen? We don't write the ionic equation next. We all right. Well, unfortunately, our HCl just killed off our precipitate. We no longer have a precipitate now. And so there's nothing to coagulate, there's nothing to digest because the HCl just ate up our precipitate. And so maybe we shouldn't add the HCl, Stanley. Maybe we should leave the HCl out. Otherwise, the HCl is going to eat up our barium sulfate precipitate, and we're going to be out of luck. There's nothing to filter. If there's no precipitate. It's funny. In Chem 1B, people always ask me, should I filter this? There's no precipitate. What are you going to filter if there's no precipitate? So that saves us day 2 and day 3's worth work. We don't have to come in anymore because we're done. This reaction doesn't happen. Why?
Barium sulfate is insoluble.
Barium sulfate is insoluble. I guess just memorize that. Barium sulfate's insoluble in HCl. Can you memorize that? What else is it insoluble in? Why don't you memorize the rest of the list? It's too much work, isn't it? That's why we have solubility rules. Solubility rules give you a pattern to memorize rather than memorizing individual reagents, of which there are thousands to remember. You want to memorize 1,000 different reagents? Every reagent we can test. Okay, if barium sulfate doesn't dissolve in HCl, will it dissolve in HBr? Will it dissolve in HI? Will it dissolve in HC? Will it dissolve in H3PO4? Will it dissolve in HNO3? Will it dissolve in... Do you want to go down a list like that and memorize it? This is why I understand, like, elementary school shouldn't do that kind of memorization because that's ridiculous. This reaction doesn't occur because hopefully you guys learned something more about double replacement reactions than what you're telling me. Uh-huh. No, that's a different kind of reaction. This is a totally different reaction than that. We don't use the activity series for this at all. But it's the same concept, though. Why we use the activity series? Why even bother with the activity series? In other words, this is, you know, there are two types of properties, chemical properties and physical properties, right? Chemical properties are chemical reactions. What are the chemical properties of barium sulfate? Simple question. What are the chemical properties of barium sulfate? Can you answer that? Do you have any clue what the chemical properties are of barium sulfate? You had one semester of chemistry. Chemistry is about properties. What can you tell me about the properties of barium sulfate? In fact, the definition of chemistry is the properties of matter, the study of the properties of matter. So is the only way to understand the properties of barium sulfate is to memorize? Let's say maybe take the 1,000 most common chemicals and then mix each one with barium sulfate to see what happens? Is that the way to understand the properties of barium sulfate? No, for chemical properties, we make our life a bit easier. We're going to talk about this in Chapter 5. But I'm a bit surprised about this, though, because I can't believe not one person can answer this. Why doesn't this reaction occur? This we say NR, which means no reaction. Why? Uh-huh.
It doesn't form a solid?
Yeah, it doesn't form a solid. Remember, in Chem 4, they tried to drill this into your head. Does it form a precipitate? Yes or no? No. Does it form a... what? Gas. Does it form a gas? No. Does it form a weaker acid from a stronger acid? Well, it's forming an acid. Is H2SO4 weaker acid than HCl? No, it's forming a strong acid from a strong acid. And so, no. Why do we look at those things? And some Chem 4 instructors say, does it form a weak electrolyte? Do you guys remember that? Does it form a weak electrolyte? Some Chem 4 instructors prefer that. Just fine. Doesn't matter. It's similar. And so, why do we do that? Those things are called driving forces. Driving forces for double replacement reactions. If we don't have a driving force, then it's not going to happen. Remember yesterday I asked you which is more stable mixture, CO2 and water or methane and oxygen? Which is a more stable mixture, methane and oxygen or CO2 and water? CO2 and water is much more stable than methane and oxygen. And so that's what drives that reaction. That reaction is driven because you're taking an unstable mixture and you're forming a stable mixture. And so every time we do this, we're looking at this. Are we forming a stable mixture from an unstable mixture or what? And so here we have no reaction. Whereas in barium carbonate, what forms here?
Barium chloride and carbonic.
Barium chloride and carbonic acid. Is barium chloride soluble or insoluble? We already know it's soluble. We see it over there. Carbonic acid. What do you know about carbonic acid? What have you memorized about carbonic acid? Well, one thing is we're going from a strong acid to a weak acid. And so I'll just write stronger acid, SA, to weaker acid. This is what we call our driving force. Therefore, we expect this reaction should occur. This one, there's no driving force, and therefore the reaction should not occur. This one, a driving force is present. But carbonic acid, you should have this memorized from Chem 4. If you don't, then you've forgotten too much from Chem 4. You've got to go back and review your notes to help you in this class, I think. But what should you have memorized about carbonic acid? Stanley? It's unstable. And it decomposes to what? Yeah, good. So you guys remember that. That's good. And so we got this bubble out. And so barium carbonate is not stable in acid. And that's why we acidify, because barium carbonate will be attacked by acid. Likewise, what do you think is going to happen to barium phosphate? Yep. And so we just balance this. 2 phosphates, 2 of these, 3 bariums, 6 chlorides. What's the driving force for this? You tell me. We're going from a stronger acid to a weaker acid. That's our driving force. Are there any other potential interfering ions? No. Well, really. Okay, we'll stop here.